Okay, next example, and it is not going to be fun, let me tell you. Well, I like it, but it's going to be a little bit intense. Pause and copy. Now, you see here the degrees are equal. In that case, you must do long division. Okay, so I do it there. And rewrite my integral and break it up into two pieces. The second piece is the unpleasant bit. If you want, you could try u is equal to denominator. It's not going to work out. So in this case, I'm going to do something different and do what's called completing the square. You'll remember completing the square from, I think it's Sec 5 that's taught. So I'm going to take my denominator, which is a quadratic, and complete the square. And that will show me a way forward. So what I do first is I isolate the x squared and the x term, and I factor out any number that happens to be in front of the x squared term. Then I will do my magical step in which I determine this number 1/4. And what you do is you take b is equal to this number in front of x here, and then b over 2 squared is a quarter. Okay, it's the quarter that ends up being added and subtracted, and notice that it's happening inside my square bracket here. Now, the magic of this method is that this trinomial here always factors the same way. It's always x plus b over 2 squared. Always the same thing. Now I'm going to multiply the 4 back through and collect all my terms together. And I get something for my integral that will help. Okay, it's going to help because now I smell an arctan, and it does not smell good, but I smell it. Because on the bottom you have something u squared plus a number. Okay, that makes me think of arctan. So what I'll do first is what's called a preliminary substitution. I'm going to do u is equal to what's in this bracket here. What this does is kind of clean up my integral a little bit. So I perform that substitution. Okay, du is just dx. And it gives me a slightly nicer looking thing. But the key here is that it's easier for me to see that I should separate this fraction into two pieces, which I did here. And the first piece, with experience, you'll see that that's a substitution. And the second piece is the arctan that I smelled earlier. Now, a word about this. Typically for a substitution, you would choose u as your new variable, but u is my old variable, right? So I don't know. You can use a w if you want, w, or often people will go t. T is equal to 4u squared plus 2. So you do a substitution. T is equal to 4u squared plus 2. And again, this is the part that looks like an arctan to me. Now, to use my memorized arctan formula, I need this 4 to not be here. So I factor the 4 out, and then I can use my memorized arctan formula to get this guy. So this is the formula for things of this form. You get some unpleasant expression involving arctan. Now in green here, I'm doing all kinds of simplifications. I'm going to simplify this and also the bracket here. And I'll also take some time down below to figure out what this is in terms of x. So all kinds of calculation fun brings me to my final answer in all its glory. Okay, next topic. So sometimes there are substitutions that are really not obvious, but work quite nicely. Now for this example here, I have this square root. Now it's not a square root that makes me think of trig sub. Okay, it's not like 1 plus x squared or 1 minus x squared. It's not something like that. So it's a kind of a non-trig sub looking square root. So in that case, I'm going to sometimes find it useful to let u equal to the square root, okay, the larger one. So that's what I do here. So I let u equal the numerator here, switching to fractional exponents. Now I'm going to do something different now than what you're maybe expecting. I'm going to take this equation and square both sides. So I'm going to get u squared on the left and something easier on the right. So I solve for x over here, and then below I'll start doing my derivatives required in the substitution. Now when you do a derivative, you can think of it this way. You're going d by dx of both sides. And the thing to notice is that the u here is an inside function. Okay, so I'm going to need chain rule. So when I do chain rule, you get the 2 coming down. Oopsie daisy. Now you have u to the 1. And then you have the derivative of the inside function there. So I'll write chain rule. Okay, now as before, I'll solve for dx. On the right-hand side, I have this u appearing still, but I can replace it by remembering what's happening up here. Okay, it's a substitution. A whole bunch more work, but here I have my u, here I have my x, and here I have my dx, so I can do everything I need to do. So for reference, the original integral was 1 plus root x all over x dx. This is my dx right here. And the numerator became u. Okay, so now we take a step to clean things up. I get this, which is a classic long division problem. So we call this rationalizing substitution because what you get is what's called a rational function as your integral. Okay, so a rational function is a polynomial divided by a polynomial. So we have this thing with all the radicals in it, and we did a rationalizing substitution to get a rational integral. We're going to leave as an exercise finishing this question. Okay, let me know if you need help with that. Here's the answer. And I'll also give you a reading exercise. Another example to look at, a simpler one. Okay, I'll say that. Example 9 here is a simpler example that you can look at and is done in full in the textbook. Okay, all that being said, the main idea here is in your bag of tricks, in your bag of tools, you have to remember that it sometimes helps to let u equal the radical or root, and that will sometimes help you out.